Hello, hello, hello. This is working. Hello, hello, hello. Yes, it's working. Cool. So where we left off from yesterday, I am going to try and understand this a bit more. So I started to read this set of definitions, and I think it just went way over my head. So let's try and go back a little bit. It says, Theorem 1. If the scalars A, B, C, D are real, so if these ones are real, we have a real four-dimensional space. And why is that? Because they result in I see. Because it's already telling us we have a vector here which is equal to the output of that. So it's just saying that if scalars A, B, C, D are real, then we do have a four-dimensional space. Okay. If they're complex, we have a complex four-dimensional space. Okay. So theorem 1. Any vector v in an n-dimensional space, I guess this thing, or this thing actually, can be written as a linearly combination of n linearly independent vectors. Yeah, okay, so that makes sense. So all it's saying is that this can be written like this. That's what it's summarizing. The proof is as follows. If there were a vector v for which this were not possible, it would join the given set of vectors and form a set n plus 1 linearly independent vectors, which is not possible in an n-dimensional space by definition. So I think it's just saying uh, you couldn't have it couldn't be true because otherwise you would have to have some additional thing suffixed to the end. Now I'm not sure about this plus one though. Um, so let's ask this question because I can't. It would join the given set of x n plus one. Oh, of course, right? Because yeah, n is the length of the set or the space. So is the length of the vector space or the set, and so adding 1 to that means there's an additional one, which can't be true. Okay, that makes sense. Definition 5. What about... Wait. What happened to the other definitions? Oh, right, here. Okay. And I can't even remember what we're trying to do here. A set of n linearly independent vectors in an n-dimensional space is called a basis. A set of n linearly independent vectors, okay, in an n-dimensional space is called a basis. So we've been working with the basis. Thus, we can write, on the strength of the above, a vector is equal to the sum of all in the set, a scalar constant multiplied by, um, so where the coefficient multiplied by a vector. Okay. Where the vectors I form a basis, where they are linearly independent. Definition 6. The coefficients of expansion vi, the coefficients of expansion vi, this one, of a vector in terms of linearly independent basis that are called the components of the vector in that basis. Okay. Um, so it's just saying that when we use the word basis, these things have specific words. These are the linearly independent vector. Uh, the coefficient is called a component when it's multiplied by the linear independent. The coefficients of expansion v1 of a vector in terms of linear are called. Okay, so it's just saying that the coefficient is called a component when we're working with a basis. Okay. Theorem 2. The expansion in equation 111 is unique. Suppose the expansion is it's unique. So let's go back to this. Whoops, zoomed into the wrong screen. Yeah, let's try that instead. I think that's... Put a little dot here. Actually, no, put a little dot here. Okay. So I'm just working with my working with my pen. So bear with me. Just gonna kind of zoom into the screen a little bit here myself. Okay, so if I remember rightly, and I don't think I do, this was the 111. So let's just double check that again. I just can't remember. So it says the expansion in equation 111 is unique. Okay, so let's go back. Equation 111 is that. Yeah, so it's the first one in our set. Okay, cool. So what does it mean for this to be unique? Ah, no, sorry, not that one. I see it now. I've even bloody written it there, haven't I? Where's my thing? There it is. This one here. Okay. What does it mean for that to be unique? It means that there are no other ways of getting it because the equation was linearly independent. That is to say that there are no combination of there is no linear combination other than a b c d 0 is 0 that can make that null vector. That's what that means. Okay. So it says suppose the expansion is not unique. We must then have a second expansion. It's saying that, well, if it's not unique, then not only do we want to sum up the n, we must have a second expansion. So I don't know what this notation really means because I've never used it before. Let's see what it says. Subtracting equation 114 from 113, i.e. multiplying the second by the scalar -1 and adding the two equations, we get this. So let's try and get that ourselves. This is 0 v minus v. Okay, this one here. Okay, so let me just try and grab that, paste it down here. Let's do that. No, let's not. Let's just actually delete this other stuff. Who cares about this? Wait, let me just get this right. This one we care about. That's one we're gonna. Let me just copy this again. I can't remember to figure out what the fuck I'm doing. So I'm gonna subtract this from 113. What's this? Can't remember what I was doing there. Okay, cool. Let's go to this line. And then we'll get this. So it says subtracting 114 from 113, we get this. Okay, so subtracting 114 from 113. Ah, we don't have 113 here. There it is. Oh, okay. Can you actually see what I'm doing here? Let me just double check this. Well, kinda. Let me zoom in a bit more. Okay, right. So if we subtract 114 from 113, we'd get V equals subtract. Oh no, sorry. We'd get E N I equals 1 Vi times I, these are the vectors here, minus sum of to n V prime I like that. So it's saying that we'd get just the negative version of that. So that's interesting. I didn't know that if you oh I didn't know if you did that. You would just get the same thing. So I'm subtracting the sum of all of a set. So the value is the sum of everything that that equation is doing, and so it would indeed be it would end up being the sum of because because we've got components in here, and this whole thing is wrapping these components, right? And then we're taking away um, different. Oh well, I can do circles. We're taking away different things. So the fact that we're taking away the sum of two different sets, we can still say that it's well whatever the sum of those things was in the components. What is the sum of these things is still just an expression. Okay, I think I'm getting this. So that's why it's just one sum symbol. The next part would be that I need to subtract, A from B. So it'd be whatever this is minus whatever this is, right? And in that case, sorry, one of these is going to be, yeah, prime like this. Let's just color that prime. And so in that case, if we have the same vector, so we've got the same vector, let's call that I, and then we are multiplying that same vector. Let's just put a little like link here or something by this and this. Ugh, can't do this very well. Okay, here we go. Then it's only the scalars. If I negate the vector itself, it'll be 0. So it's only the scalars that really matter. And that's why the equation ends up being now I wonder if I would have known that myself, but it's good to see it anyway to remind myself that's how things work. So and therefore it's basically this, right? Exactly what they've put. V I minus V prime I, and then we can multiply it by the set, and it's bod mass. So the multiplication would happen first. We'll have to make sure that this is done first to I. And we've ended up with what they've got. Okay, cool. So that makes sense, doesn't it? So let's go back to this, which implies that Vi is equal to Vi, since the basis vectors are linearly independent and only a trivial linear relation between them can exist. Because whatever you were to remove from that, you'd end up with a constant, which a coefficient, a scalar coefficient, which is still it's still going to equate to the same equation, right? Let's make this something different. So I think it's what it's saying is so like therefore it would be, you know, vi minus vi could be a, and then you're back to square one, because it just makes another thing, right? And in that case, well, look, this is exactly the same as saying this. I think that's what that's saying. Since the basis vectors are linearly independent and only a trivial linear relation between them can exist, note that given a basis, the components are unique. So because it's linearly independent, the components are unique. The coefficients are unique. And so if we add another one, it still doesn't matter because it's still unique and it's still multiplying by the original one. But if we change the basis, the components will change. We refer to vector as the vector in the abstract, having an existence of its own and satisfying various relations involving other vectors. Let me read that again. We refer to vector as the vector in the abstract, having an existence of its own and satisfying various relations involving other vectors. Okay. We choose a basis. The vectors assume concrete forms. Oh, when we choose a basis, the vectors assume concrete forms in terms of their components, and the relation between vectors is satisfied by the components. Imagine, for example, three arrows in the plane. So let's do this. Let's imagine this. So I need to move my screen along. Got my bottom dot there. Okay. I've got my bottom dot here, and let me just draw. That. Yeah, perfect. Okay. And let's move this over to here. And let me sip my coffee. Okay, right, cool. So it says, where are we? We're here. Imagine, for example, three arrows in the plane. Okay, so let's draw a plane. Here's our plane. Imagine three arrows in the plane, A, B, and C, satisfying A plus B equals C. So let's say we want to make this C. This is C. Well, let me label it in the middle because I always do this and I end up realizing that I wanted the endpoint to do something and then I've got the C there. So let's imagine that's our vector. Now A plus B equals C. So I guess this one is A, and this one is B, right? Haha, yes! I win, I win, I put it in the right place. Now it says, um, according to the laws for adding arrows, so far no basis has been chosen, and we do not need to make a basis to make the statement that the vectors form a closed triangle. It's a typo. Now we choose a basis and write each vector in terms of the components. Now we choose a basis and write each vector in terms of the components. Now we choose a basis. So this is linearly dependent. This is linearly dependent because A and B do make C. Let me think. Yeah. Um, I think that's right. I think that's right. Let me just GPT that because I don't want to move forward if I'm completely wrong here. Um, if I were to plot three lines, three vectors, A, B, C, so that they satisfy A plus B equals C, then am I right in thinking that these would form a linearly independent, no, dependent set because C is redundant in that set. This is in regards to definition 6 in Principles of Quantum Mechanics by R. Shankar. Yes, that's correct. In the situation where A plus B equals C, the set of vectors would indeed be linear dependent. The reason for this is that you can express one of the vectors, C in this case, as a linear combination of the other vectors. In other words, C doesn't add any new direction that isn't already spanned by A and B. It's important to remember that in the context of quantum mechanics, these vectors represent states of a quantum system. So a set of linearly dependent vectors means that some of the states can be expressed as combinations of the others, reducing the number of truly distinct states in the system. Okay, cool. We've got it so far. We are doing well. Let me get my thing back up. Oh, hey. Now we choose a basis and write each vector in terms of the components. The components will satisfy C equals A plus B. So let's go here. Sorry about my sniffing. I've got a little bit of pollen. Hay fever. So it's saying now we're going to choose their components. So these are the coefficients, the scalar coefficients, right? If we go A plus, I hate this. I'm saying it to you, the viewer, if you ever watch this. But unless you've watched the last video, you would have no idea what I'm talking about. And what's more funny is that I myself, when I watch this next time, if I come right into this video, I will have no idea what I'm talking about. So I'd have to also go to the latest video. the last video. So I apologize. I suppose I'm just going through this myself, assuming that like whoever's watching is just in a flow state, just watching someone do work. Because otherwise, my learning will go nowhere because I'll be explaining myself again and again. The components will satisfy C equals A plus B, and um, where I equals 1, 2. Yeah, okay. So it's saying let's imagine this is a vector, a matrices, sorry, matrix. Um, it's just saying that the ith element, actually, I think it's the other way around. I think it's this one, is 1, 2. I think that's right. And this would be J, right? 4, 6. Column vectors. Yeah. If we choose a different basis, the components will change in numerical value, but the relation between them expressing the equality of C to the sum of the other two will still hold between the new set of components. So if we form a basis, then they must be linear independent. It's saying that the components will satisfy that. Maybe this is not quite right. Let me continue on. So far, no basis has been chosen, and we do not need a basis to make the statement that the vectors form a closed triangle. Now we choose a basis and write each vector in terms of the components. The components will satisfy C equals A plus B, I equals 1, 2. If we choose a different basis, the components will change in numerical value, but the relation between them expressing the equality of C to the sum of the other two will still hold between the new set of components. In the case of non-arrow vectors, adding them in terms of components proceeds as in the elementary case thanks to the axioms. If the sum of all coefficient scalars, if the product of the coefficient scalar to a vector, so if the product of a coefficient scalar to the vector and the sum of all infinite amounts equals the vector, and another vector is the sum of all a different coefficient, then we end up with vector plus vector equals the sum of all v plus w. Yeah, that's true. That makes sense. And it's good because we drew this before. This notation that we have these different components, and so if we were to scale them and stuff, the addition, the subtraction, all that stuff doesn't make a difference. So I would agree with that. That makes sense. Um, So where we have used the axioms to carry out the regrouping of terms, here is the conclusion. To add two vectors, add their components. There is no reference to taking the tail of one and putting it on the tip of the other, etc. Since in general the vectors have no head or tail. Of course, if we were dealing with arrows, we can add them either using the tail and tip routine or by simply adding their components in a basis. In the same way, we have um, the coefficient scalar multiplied by the vector is equal to the coefficient scalar multiplied by the sum of all new unique coefficient scalars multiplied their vectors. Oh wow, okay, that's interesting. So can you actually see this on the... Yeah, I think you can roughly see it. I can't make it any bigger, basically, because Amazon doesn't let me zoom into the to the book I bought. Annoyingly, look, I try and zoom in, and it just kind of resets it. I could disable the event, I suppose, but well, it is what it is. Oh, actually, maybe I can. Maybe, perhaps I can. Okay, that gives us a bit more. Cool. Is that a little bit bigger? I didn't see if it resized. Sorry. Just waiting to see. No, it didn't. Ah, well, shame a shame. Okay, well, it says because it's not a line that you can add things to and get a resulting scale. That's not how we should envision these. These are quantum states, right? Because they're represented by this vector thing, or they are just an object. And so, how do you visualize an object that has so many dimensions? You can't just draw a line, right? Well, maybe you can. Um, and so you have to take the axiom to prove that it's true. Good, I understand that. And it says, if we are dealing with arrows, we can add them together, of course. In the same way, we have this. So this is equal to the sum of all vectors because the sum. I see. Yeah, it's equal to. Oh wow. Okay, that's interesting. Let's write this down because that's quite interesting. Let me just make this a bit smaller. Give me some. Give me some space. So it's saying that. Oh, come on, whiteboard. Stop pissing around, please. Okay. A vector is equal to the sum of, like, I. It's saying a vector, and that's all. Is that right? Sorry. Let's do that again. A sum of vector I is equal to the sum of I a v I multiplied by the I vector, ith vector. So how does this work? It's saying that if you were to multiply the sum of it or add it as a coefficient to all of them, they are equivalent. Let's put some numbers in here. So if I were to do the sum of um, let's do that where I equals 0, then let's just do I. That would equal 3, and let's times that by 2, right? So 2 times 3. Sorry, let me do it again. Let's do this as O for output equals to 3. And then we do AO, where A is 2. So let's do 2O would equal 6, right? Now, let's do the other way. If you were to do O, no, if we were to do, yeah, if we were to do O times I, and do the sum of that, then, this isn't O by the way, not 0. In fact, let's call it Z. 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 And then we'll do Z. No, we don't want to do that. We want to do 2y, 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 2y. So now, 2 times 0 is 0, 2 times 1 is 2, 2 times 2 is 4, 2 times 3 is 6, 10, 12. So this one would equal 12, whereas this one is 1, so 0 plus 1 plus 2 plus 3. So this would equal 6. And then we can times that by 2, which equals 12 as well. So they are equivalent. Okay, that's good to know, right? That's fine. In other words, to multiply a vector by a scalar, multiply all its components by the scalar. Okay, cool. That's good understanding. Uh, new chapter, new section. Yoo! Okay, cool. We are making progress. Inner product spaces. Whew. The matrix and function examples must have convinced you that we can have a vector space with no preassigned definition of length or direction for the elements. Yes, we can work entirely with the axioms that we've created so far about linearly independent and dependent vector spaces and totally satisfy our unquenched thirst to know that this is true. I agree. However, we can make up quantities that have the same properties that the lengths and angles do in the case of arrows. The first step is to define a sensible analog of the dot product for in the case of arrows from the dot product. Wait, what? You know, there was this typo just before, so now I'm like trying to reshuffle the words in my head to make a clear sentence, and maybe that's not what I should be doing first. Let me just read this again. The first step is to define a sensible analog of the dot product. For in the case of arrows, from the dot product. So here's a dot product. We can read off the length of, say, A as the square root of the dot product of A, and the cosine of the angle between two vectors as the dot product of A and B. Oh, the dot product of A and B multiplied by the magnitude of A. Oh, I see, divided by. So the dot product of A and B divided by the magnitude of A and B. Now, you might rightfully object. How can you use the dot product to define the length and angles if the dot product itself requires knowledge of the lengths and angles? That's right, because the dot product requires magnitude. The answer is this. Recall that the dot product has a second diagram equivalent expression in terms of the components. It's saying that the dot product of A and B is also equal to the multiplied. Oh yeah, of course. Oh, that's obvious. Our goal is to define a similar formula. Oh, that's fascinating though. Wow. Oh, mathematics. Blow my mind yet again. It's wonderful, isn't it? Because now we've established that the linear combination of all vectors can form that linearly, or can diagnose linearly or independent, linearly dependent or independent vectors. Therefore, we can use the same thing when we're trying to do a dot product. That's amazing. Our goal is to define a similar formula for the general case where we do have the notion of components in a basis. To this end, we recall the main features of the above dot product. Symmetry. There is symmetry. Okay. The A vector, the dot product of A, is greater than or equal to 0 if this is interesting. This double F, I've never come across that. What does if mean in mathematics? Is it equivalent to if? If and only if. It's a stronger condition than if. When you say P if Q, it means that Q is true, then P is also true. However, P could still be true even if Q is false. On the other hand, when you say P if and only if Q, it means that P is true if Q is true, and P is false if Q is false. In other words, P and Q are exactly equivalent. To put it another way, if and only if means that P implies Q, and Q also implies P. The conditions P and Q are linked in both directions, not just one. Okay, that's good. Glad I looked that up. So 0 if and only if A is equal to 0. Positive semi-definiteness. Semi-definiteness. Definiteness. Okay, it's too abstract at the moment. A multiplied by, no, A, is this multiplication or dot product? Yeah, it's just dot product. So the dot product of A and a scalar coefficient to B and C is equal to B, A, linearity. Oh, that's a bit more difficult. So I'm gonna have to stop here though because I actually need to go somewhere. Oops. Let me just write this down. So it's saying that A dot product to B vector plus C some scalar coefficient C vector is equal to B A vector dot product of B vector plus some scalar coefficient A dot product of C. Okay, and why is that so? Because why is that so? Because the dot product on A and B makes another vector, I guess. We could say Z here plus Y is going to equal to was that A? Was A? Yeah, vector. Sorry about that. Is going to be equal to Z dot product of B plus C. Whoa, this is blowing me out at the moment. C. Let me just do this for a second, it's a bit easier to read. Oh man, I actually don't see that yet. We could work through it. I think I'm in a bit of a rush and need to go somewhere. Let me just read on a little bit more. The linearity of the dot product is illustrated in figure 1.2. Do we have a 1.2? We don't have a 1.2. Maybe it's forward. We don't have a 1.2. Great. Oh, here it is. Ha, sorry. Oh, I see. Okay. We want to invent a generalization called the inner product or scalar product between any two vectors, v and w. We denote it by the symbol vw. It is once again a number, generally complex, dependent on the two vectors. We demand that it obey the following axiom. So let's do this page again next time. But thanks for watching if you did, and